We noted in the previous video that the reaction rates of many chemical reactions depend on the concentration of the reactants. In this video, we look at the relationship between concentration and rate in more detail and introduce the concept of rate laws. Experimentally, we can study the effect of concentration on the reaction rates by noting how the initial rate of reaction changes when we vary the initial concentration of reactants. As an example, let's look at the gas phase reaction of the production of chloral fluoride, ClO2F, from the reaction between elemental fluorine and chlorine dioxide. We can show a plot of concentration versus time for both reactants and products, which show that as the reactant concentrations of F2 and ClO2 decrease, so the concentration of chloral fluoride increases. For a given set of starting concentration of reactants, we can measure the initial rate of formation of products, which is taken as the instantaneous rate at time t equals 0 and is measured as the slope of the initial part of this curve. This table shows some experimentally derived rate data for this reaction, where we can see that 6 different experiments were carried out, and in each experiment, the initial rate was determined for 6 different combinations of starting concentrations of reactants. In the first 3 experiments, the concentration of F2 was kept constant at 0.10 molar, while the concentration of ClO2 was varied. We can see that as the concentration of ClO2 was doubled by comparing the results from experiments 1 and 2, the rate of reaction also doubled, and when the concentration of ClO2 was tripled, comparing experiments 1 and 3, the rate of reaction also tripled. This suggests that the rate of reaction is linearly proportional to the concentration of ClO2, and we can represent that with a mathematical statement as rate is proportional to ClO2 concentration at the bottom left of the screen. In the last 3 experiments, the concentration of ClO2 was kept constant at 0.10 molar, while the concentration of F2 was varied. This time we can see that as the concentration of F2 was doubled, comparing experiments 4 and 5, the rate of reaction again doubled, and as the concentration of F2 was tripled, comparing experiments 4 and 6, the rate of reaction again tripled. This suggests that the rate of reaction is linearly proportional to the concentration of F2, and we can again represent that with a mathematical statement as the rate is proportional to the F2 concentration, shown at the bottom left of screen. Combining both observations, we can say that the rate of reaction is proportional to both the concentration of F2 and the concentration of ClO2, and we can make this proportionality expression an equality by including a proportionality constant K. And this expression here is a specific example of what we call a rate law. A rate law is an expression that relates the rate of a chemical reaction to the concentration of reactants. For a general reaction of the form A plus B going to C plus D, where the lowercase letters represent the stoichiometric coefficients, the rate law will take the form of rate equals K times the concentration of A raised to the power m times the concentration of B raised to the power n, where the exponent n is referred to as the reaction order with respect to reactant A, and the exponent n is termed the reaction order with respect to reactant B. The overall reaction order is given by the sum of the individual reaction orders, m plus n. In the rate law that we experimentally determined just a moment ago, the exponents for F2 and ClO2 were both 1. Exponents of 1 are not explicitly shown in rate laws, and we will examine the exponents in rate laws in more detail in a moment. The proportionality constant K in a rate law is called the rate constant, and the value of K is constant for a particular reaction at a particular temperature. The magnitude of K can be determined by rearranging the rate law to make K the subject of the mathematical expression, and we'll see how to put that into practice in the next video in this series. For now, however, it is very important to note that rate laws must be experimentally determined and cannot simply be written down from a balanced chemical equation. We determine the rate law from experimental data that includes rate and concentration information using the type of approach we just employed a minute ago. Again, we'll get more practice with this in the next video in this series. Before that, however, it's important we get our terminology correct when talking about rate laws. For the general chemical reaction A plus B goes to C plus D, the rate law shown has exponents of m and n, and these are called reaction orders. For the specific reaction we have just seen between fluorine and chlorine dioxide, we determined that the values of m and n were both 1. Remember, we do not explicitly write the number 1 in rate laws. The terminology we use is to say that this reaction is first order with respect to F2 or first order in F2. And this is an individual reaction order for a reactant. The reaction is also first order in the other reactant, ClO2. The overall reaction order for this particular reaction is second order, given by the sum of the individual orders for each of the reactants involved. In the general case, the overall reaction order is equal to m plus n. For the most part, individual reactant orders of reactants are typically whole numbers, and most are first order or second order. For some reactions, however, fractional reaction orders are possible, and reaction orders of 0 or even negative values are also possible in rare cases. The individual rate orders, or the exponents in a rate law, tell us how the rate of reaction is affected by the concentration of each reactant. For example, if the exponent for reactant A is 1, that is, the reaction is first order in reactant A, then the rate of reaction is directly proportional to the concentration of A. And doubling the concentration of A will therefore result in the rate increasing by a factor of 2, or 2 to the power of 1, 1 being the order of reaction with respect to A. Likewise, tripling the concentration will result in the rate increasing by a factor of 3, or 3 to the power of 1, again 1 being the order with respect to reactant A. If, however, the exponent for reactant A is 2, that is, the reaction is second order in reactant A, then the rate of reaction is proportional to the concentration of A squared. In this case, doubling the concentration of A will result in the rate increasing by a factor of 4, that is, 2 to the power of 2, where the exponent 2 is the reaction order for reactant A. And tripling the concentration of A will result in a rate increase by a factor of 9, that is, 3 to the power of 2, again 2 being the order with respect to reactant A. If a reaction is 0 order in a particular reactant, the rate is independent of concentration, and changing its concentration will have no effect on the rate, since any concentration raised to the power of 0 is equal to 1. In the next video, we will look more closely at deriving rate laws from experimental data, and we will note these patterns shown here relating to rate changes when we double or triple the concentration of specific reactants.